Okay, in this video I want to talk about the evidence for our modern picture of the universe and its evolution over time. And I want to focus on what we've just been talking about in the past few videos, which is what are the tools that astronomers have at their disposal for figuring out things about the distant objects in the universe. And so I'm going to do this a little bit differently than I usually do it and focus really intently, or try to, every step of the way on talking about evidence. We have to go pretty far back to talk about our the origin of these cosmological ideas, because our picture of the scope of the universe actually changed a lot in the early part of the 20th century. In the 1700s and 1800s, our view of the universe was that the Milky Way, this stripe of stars that we see that crosses the sky at night, was the universe. That all the stars that we see in the Milky Way made up all the stars in the universe. In the 1700s, William Herschel, the guy that discovered Uranus, mapped the locations of all the stars in the sky as best as he could, basically using a few parallax measurements, but mostly just guessing how far away stars are based on their brightness. And the map he came up with has the sun in the center, that's our sun, and all the other stars making this kind of flattened blob around it with us in the center. There's a little split in the blob over here. That dark space is the dark gap you see in the Milky Way when you see the Milky Way up in the sky. What Herschel did not know, what Herschel had no way of knowing, that the stars we see in the sky are just the tiniest piece of the stars that make up the Milky Way galaxy. The Milky Way galaxy extends tens of thousands of light years beyond where the most distant stars that Herschel could see with his telescope and his eyeball, which was the only tool available at the time for looking at space. You had a telescope, you put your eye up to it, you drew pictures of what you saw. Another thing that we discovered in the 1800s when looking at the sky are lots of nebula. Nebula is a word in astronomy that means almost nothing. A nebula just comes from the word for cloud. So anything that when you look through the telescope, you see a little cloudy blob of light is called a nebula. Some nebulas are places where stars are being formed. Some are places where stars have blown up. Some are just diffuse gas in between the clouds. And some are little tiny spirals. And there was a debate in the 1800s and early part of the 20th century about what these little spirals are. What are these little spirals of light we see in our telescopes? There were two camps. One is, well, these are just little swirling gas clouds here in our Milky Way galaxy with all the stars that we see in the sky. The other was that these little swirls of light that we see through our telescope are whole galaxies like the Milky Way, but they would have to be located very far away to only show up as little swirly clouds in our telescopes. So the spiral nebula hypothesis was just, these are little swirly gas clouds that are located close to us. The island universe, which was an old-fashioned name for galaxy, hypothesis was that these spiral nebulas are other things like the Milky Way, which consist of millions or hundreds of millions or billions of stars. In the late 1800s, early 1900s, there was no way to tell the difference between these two pictures. The spirals are close, the spirals are far away, because there was no way to measure the distance to them. So there was an actual debate about these two interpretations of these little spiral swirls that we see in our telescopes. There was actually a literal debate called the Great Debate, or the Shapley-Curtis debate, which was held in 1920 at the Museum of Natural History up in D.C. Some of you have maybe been there. Between Harlow Shapley and Haber Curtis. I always forget which is which. Curtis said that they were independent galaxies located far from the Milky Way, and Shapley said that these are just little spiral gas clouds inside our Milky Way galaxy. There was no evidence for either of these ideas as of 1920. You don't have debates about things that there's evidence for, right? If there's a debate, it's because there's no objective way to decide between them. A few years later, we were able to find evidence. It turns out that Curtis was right. The distant nebulae are distant, and they are galaxies like our Milky Way. Where did that evidence come from? It came from Edwin Hubble, who we have nowadays named a telescope after. Hubble was one of the earliest scientists using observatories to do photography of stuff in space. Once we had photography available to us, we were able to get photographs of much dimmer and dimmer and dimmer stars than you can see with your eye. In a photograph of the Andromeda Galaxy, Hubble identified Cepheid variable stars. It was already known by the 1920s that Cepheid variable stars have this relationship between their brightness and their period. Hubble measured the period of some stars in the Andromeda Galaxy, figured out how bright they really were from their brightness curve, and realized, oh wow, these stars in the Andromeda Galaxy are really, really, really far away. And that's how Hubble established the modern scale of our universe. The distance to the Andromeda Galaxy is millions of light years. So from 1920 to 1930, the universe got hundreds of thousands of times bigger once we realized that every one of these little spirals that we see in our telescope is a distant galaxy that is millions, or in some case billions, of light years away. This is a huge revolution. What is the source of the revolution? It's the use of standard candles to measure the distance to very far away things, which we could not do until we, first of all, knew about this relationship, and second of all, had the tools to actually measure those stars. Nowadays, our picture of the universe is that it consists of billions of galaxies, or possibly even hundreds of billions of galaxies, separated by millions or billions of light years. This is one of the most famous pictures in the history of astronomy. It is the Hubble Deep Field image of galaxies. It encompasses an area of the sky about the size of your pinky fingernail. If you go out at night and hold your pinky finger up to the sky, the size of your pinky fingernail is about the size of the field of view of this camera. And everything, almost everything you see in this picture is a galaxy, except for that's a star. In our galaxy, it's like a speck of dust on our glasses. That's a star. But every one of these tiny, even the tiniest little smudges of light in this picture is a galaxy. There are thousands of galaxies in this picture. And our modern picture of the universe says that these galaxies are, over time, getting further and further and further apart from one another. And we call that idea that the distances between the galaxies are increasing. We call that idea the Big Bang theory. Where does that theory come from? What observations and evidence is it based on? Once Edwin Hubble was able to measure the distances to galaxies by looking for stars in them, he was able to plot their distance on a graph. The other thing he did was to look at the spectra of the stars in those galaxies. He found some spectral lines and noticed that, take these two, hopefully you can see these, there's two little dark absorption lines in the spectrum. And in each photograph, as we go to galaxies that are further and further and further and further away, these spectral lines are shifted further and further and further to the red end of the spectrum. This means that if we interpret this spectral shift in terms of the Doppler effect, which remember tells us how fast something is moving, that all of these galaxies are moving away from us because their spectral lines are all red shifted. Right? When something's moving away, the wavelengths get stretched out to longer wavelengths. That corresponds to the redder end of the spectrum. So Hubble discovered that every distant galaxy, not Andromeda and the Milky Way's little friends in the local group, but all the distant galaxies beyond our local group are all moving away from us. What does that mean? Well, first of all, is there a relationship between these two things? There's actually a mathematical relationship. So this is around 1929 that Hubble makes this discovery. And what he discovers is that all the galaxies are moving away, and not only that, but the further away the galaxy, the faster it is moving away from us. And this is the raw material for what will become the Big Bang model of the universe. You can actually make a graph of how fast the galaxy is moving as a function of how far away from us it is, and that graph is roughly, at least to our best of our ability to be able to measure these things. Remember, measuring distances is hard. in astronomy, but roughly a straight line. A straight line in algebra class is y equals mx plus b, right? This straight line relationship between velocity and distance is velocity equals some constant times the distance, and we call that constant h, the Hubble constant. So the Hubble constant is just the slope of this line. Okay? If the Hubble constant is big, this line would be big. If the Hubble constant was small, that line would be lower, less slope. That's just an observed relationship from looking at galaxies, measuring their speeds, measuring their distances. It's what we call an empirical law. An empirical law is one based on observation. But what does it mean? What does it mean that the galaxies are moving faster and faster and faster as we look further and further and further away? And remember, when we're looking far away in astronomy, we're also looking back in time. Well, what we take this to mean is that the universe as a whole is expanding, that every galaxy is getting further away from every other galaxy. So the universe is, quote unquote, expanding. That is, all the Big Bang Theory says, that the universe is getting bigger and bigger and bigger as the distance between distant galaxies gets bigger and bigger and bigger. But it says something a little bit more than that. If we take that observation, and it is an observation, if we take that observation of the receding galaxies seriously, if everything's moving apart now, that means in the past everything was closer together. Right? Which means in the past the universe was smaller and denser, more material in a smaller space. If you take more material and put it in a smaller space, it also gets hotter. So the universe expanding in the present suggests that in the past the universe was smaller, 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 hotter, 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 denser, 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 until you get back to a point where the universe was very small, very hot, very dense. And how far back can you go? Can you go all the way back to the point where everything in the universe was in a sphere this big, the size of a softball, the size of a marble, the size of a ball bearing, the size of a pencil point? Maybe. That's what the Big Bang Theory suggests as an extrapolation of the observation. But the observation is taking place in the present. All the distant galaxies are moving apart. We can tell that with the Doppler shift. We can tell their distance by using standard candles like Cepheid variables and supernovas. And so the observational evidence for this current expansion is very strong. The extrapolation back to some distant time is a theory that needs to be tested and needs to have its predictions confirmed. What is one prediction of this theory? Well, first of all, what does it mean that all the galaxies are getting further and further apart from one another? Your first reaction is probably, if all the galaxies, when we look out in space, are moving away, doesn't that make us the center of the universe with everything moving away from us? No, that's not the case. I've taken just a little chunk of the Hubble picture and I've colored two of the galaxies, one yellow and one blue. I'm going to expand this by making it bigger and bigger. Now, if I take these bigger and bigger pictures and stack them on top of each other, whatever galaxy I live in, I'm always in the same place. Right? So let's imagine we live in the yellow galaxy. I'm going to stack these growing pictures on top of each other with the yellow galaxy always in the same place. Okay, so bigger, 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 bigger. That's what that looks like. So as this picture gets bigger, as the galaxies move apart from one another, if you are in the yellow galaxy, it looks like all the galaxies are moving away from you. But what if we lived in the blue galaxy? What would this look like? If I take those same expanding pictures and stack them on top of each other with the blue galaxy always in the same place, it looks exactly the same. If you are in something that is expanding, no matter where you are, when you look out around you, because everything's getting further apart, it looks to you like you are in the center of the expansion. Everything is moving away from you. So the Big Bang Theory doesn't say that the universe is expanding from here, or from any particular point in the universe. Everything in the universe is moving away from everything else. There need not be any center to the expansion if the whole universe is expanding. Now, what's one of the predictions of this theory? Remember when we talked about black body radiation? All objects give off light depending on their temperature. If I heat an object up from red hot to yellow hot to white hot, it gives off more and more high frequency, high energy radiation. and more radiation in general. It gives off more light, but it also gives off bluer, more violet, more ultraviolet light as it heats up. That phenomenon is called black body radiation, the radiation given off by a body just due to its temperature, whatever that temperature is. And we talked about the fact that this extends all the way to the lowest energy light at the radio end of the spectrum, all the way up to the highest energy light from the X-ray, gamma ray end of the spectrum. If we take this Big Bang picture of the history of the universe seriously, and we believe that in the past the universe was very small, very hot, very dense, we can calculate the temperature of the universe, what it would have been at any point during this expansion. Just take the amount of energy in the universe now and squish it into a smaller space. There would have been a point in history where the universe was so dense, there was so much stuff everywhere, that light couldn't actually travel from one place to another. The universe would have been opaque, like a star. You wouldn't be able to see through it. We can calculate when that transition would have happened, and when light would have started traveling around the universe. When the universe went from being too dense for light to go anywhere, because it's like being inside of a rock, to spread out enough that there's space enough between the atoms for light rays to move around. We can calculate what temperature that would have happened. It would have happened at a temperature of billions of degrees. There would have been a phase in the early universe where the universe was so dense that it was opaque, but we can calculate when that transition would have happened from being opaque to transparent, from light just going from one atom to the next atom to light being able to go between the atoms and start moving around the universe. Some of that light from that time in history, that's a time we call recombination. We'll get into the details of that some other time. Some of that light should still be in the universe, should still be bouncing around the universe like an echo. We can calculate what the temperature or the corresponding black body wavelength or frequency of that light should be. It would have been very hot gamma ray X-rays, but over time as the universe has expanded, we're looking at those faraway galaxies and the spaces between those galaxies. That light has gotten red shifted all the way down beyond red to the microwave portion of the spectrum, corresponding to a temperature of 2.7 degrees Kelvin. It's only 2 degrees, or a little less than 3 degrees above absolute zero, so very low temperatures. The universe used to be billions of degrees. It has cooled off to just a few degrees above absolute zero. So this light should be bouncing around the universe still today. We call this hypothetical, for now, light the cosmic background radiation. And it's in the microwave area of the spectrum, so we sometimes call it the cosmic microwave background radiation. By 1950 or so, scientists realized if the Big Bang theory was correct, if the universe really did used to be small and hot and dense, there should be microwaves bouncing around the universe, red-shifted, leftover light from the time in history when the universe just went from being opaque to transparent. It's a prediction. We should see this light, and it should correspond to the temperature we calculated from our theory of black body radiation. The story of the discovery of this radiation is interesting. I won't go into the details. Suffice it to say, it was discovered entirely by accident by two scientists, Penzias and Wilson, who worked for Bell Labs. Bell Labs was a communications company back in the 1960s. You might associate the name Bell with telephones, like Alexander Graham Bell. That's where the name Bell Labs came from. A communications company, and they were experimenting with using microwaves. This thing behind Penzias and Wilson, this big horn here, is a microwave receiver, and they were using microwaves for communications. Nowadays we use microwaves for communications. That's what your cell phone transmits and receives, is microwaves. This was a much bigger antenna than your cell phone. This big horn gathered the microwaves and they bounced around in here to the receiver behind this guy's head here. Penzias and Wilson discovered that no matter where they pointed their microwave receiver, they always got a signal. They always got like static microwaves coming from somewhere. They tried to figure out where it was coming from, and they couldn't. They tried to figure out if it was coming from people's televisions or people's cars starting up. That didn't seem to be it. They tried to figure out if it was interference caused by the fact that there were pigeons living in the receiver, doing what pigeons do in an enclosed space. They shoot all the pigeons out. They cleaned all the pigeon. They cleaned out the inside of the microwave receiver. still static, still noise. They couldn't figure out why the receiver was picking up the static until they happened to be talking to an astronomer one day who said, hey, are those microwaves coming from every direction? And they said, yeah. And the astronomer realized that could be these microwaves that the Big Bang Theory predicts should be bouncing around the universe. And they are. This is a map of the sky in microwaves. How do we get this map? We had to build a microwave telescope. Where do you have to put a microwave telescope? You have to put a microwave telescope in space. And it's a complicated mess. This stripe across the middle is the Milky Way galaxy. By the way, what is this? Why is this an oval like this? This is the whole sky, 360 degrees around, all the way around, top, bottom, front, and back. You've probably seen a map of the Earth where the whole globe of the Earth is projected into an ellipse like this. This is the same thing but for the sky. So this is the whole sky projected into an ellipse, with the Milky Way being the axis that we've chosen to make the axis of the ellipse. So this light that makes a kind of a stripe across the sky like this is actually just a tilted circle. It's the plane of our solar system. This light is light reflected from little bits of dust and ice and stuff in our solar system. It's called the zodiacal light. You can actually see this if you go someplace very, very dark. It looks like sort of a cone of light, usually towards the south in the sky. I've never seen it, but I hear you can see it. We're not interested in that. So we use a computer and say, take that out. Take out the zodiacal light. So now, this is just microwaves coming at us from outside our solar system. Take out all the scattered junk from inside the solar system. Well, this is the Milky Way galaxy. We're not interested in light from the Milky Way galaxy. We want to see the microwaves coming from between the galaxies, from the distant space that corresponds to beyond the observable galaxies. So we take a picture of the Milky Way galaxy, and we subtract away where all the light is coming from. So this is the microwave that's not coming from stars and gas and junk inside our Milky Way galaxy, but it's coming from outside the Milky Way galaxy. The extragalactic background. Now the black spaces here are just stuff that's blocked by our view of the Milky Way. There's nothing we can do about that. Some of the microwaves in this picture, though, are coming from galaxies. That's not what we're interested in. We're not interested in the microwaves coming at us from galaxies. We're interested in the microwaves coming from before there were any galaxies. So we take a picture of the sky, like the picture from the Hubble with all the galaxies in it, and we subtract away all the light that's coming from a galaxy. And we get a map that looks like this. The map of the cosmic microwave background. These are microwaves that are not coming from the solar system. They're not coming from our galaxy. They're not coming from other galaxies. They are coming from between the galaxies, from a point in space where there is nothing but hydrogen gas that existed 13.5 billion years ago. What do we see? We see places where there's a little more microwave intensity, the brighter places in this map, places where there's a little less microwave intensity. We can measure the spectrum of these microwaves and see that they correspond to the temperature that would you expect. At what temperature would the universe have cooled off enough for light to travel around? The spectrum we get when we do this looks like this. It looks like the black body curves I've showed you all along. The wavelengths of this microwave background radiation agree precisely with the predictions of the Big Bang. This is not a theoretical curve. This is data of our measurements of the intensity of the cosmic microwave background at different frequencies, giving us a black body curve. This is from a satellite called COBE, C-O-B-E, the Cosmic Background Explorer. This satellite released its results in the early 1990s. I was an undergraduate, like you, in the early 1990s, majoring in physics, and our physics department that year, I went to physics at Towson. I went to undergraduate, I got my PhD from William & Mary, but my undergraduate school was Towson University in Maryland. We drove from Baltimore down to Washington, D.C., where the American Physical Society was having its annual meeting. One of the presentations at the American Physical Society meeting that year, it was 91 or 92, I'd have to check Wikipedia to see, 91 I think. One of the presentations was the results of the Cosmic Background Explorer satellite. There were news trucks and news cameras there. It was a big deal. Why? This was the first measurement of the spectrum of the cosmic microwave background. Penzias and Wilson discovered that it was there in the 60s, but in the 1990s, we actually measured its spectrum and found that it corresponds exactly to the predictions of the Big Bang model. Okay. Kobe, 1992. This is, again, a map of the intensity of microwaves coming at us from different directions in the sky. The difference in intensity between the hottest spots and the coldest spots, that's what these intensities are a map of, places where there's lots of microwave radiation, places where there's little. The difference in temperature is about 1 part per million, about a millionth of a degree Kelvin. So these are very tiny fluctuations in temperature and density. This is essentially a map of the universe when it was just a few 100,000 years old. Where was it hottest? Where was it coldest? Since then, in 2003, we launched a satellite called WMAP, which stands for the Wilkinson Microwave Anisotropy Probe, which is a lot of big words. Wilkinson's just a dude. Microwaves are what it observes. Anisotropy. So if the microwave radiation coming at us from all directions was exactly the same intensity and temperature everywhere, we would say that that radiation was isotropic. Isotropic means the same in every direction. The microwave background is almost isotropic. The variations are just 1 part in 100,000, but there are variations. What this satellite is measuring is the amount that the radiation is not isotropic or anisotropic. So the Wilkinson Microwave Anisotropy Probe is measuring the tiny fluctuations in temperature and density of the early universe by measuring the fluctuations in intensity of the cosmic microwave background radiation. These fluctuations are important. If this picture was all the same color, all the microwaves coming at us from every direction in space were all the same temperature, that would mean that 13.5 billion years ago, all of the hydrogen gas that was giving off those microwaves was all the same temperature and all the same density. If, when the universe was a few 100,000 years old, it was all the same temperature and all the same density, as it expanded, it would still be all the same temperature and all the same density. The universe would be a uniform soup of hydrogen gas, because if there weren't places that were a little bit denser than others, what happened in these little bit denser places? What happened is there's more matter there, so gravity starts to pull those things together, and gravity starts to pull in material from around there. And it's these dark regions in these maps that wind up being galaxies and clusters of galaxies and superclusters of galaxies. The more dense regions have more mass, so they pull matter in from the less dense regions. So you need these little fluctuations in density and temperature to give us a universe that looks like our universe today. Our universe today is not a uniform soup of hydrogen gas. It has a lot of lumpiness. There are clusters of galaxies, and within those clusters there are lumps called galaxies, and within those galaxies there are lumps called planetary systems, and within those planetary systems there are lumps called planets. On those planets there are lumps called human beings. The difference in density between you and the air around you is huge. Right? The difference in density between Earth and the space between the Earth and the Sun is huge. The difference in density between the Sun and the spaces between the stars is huge. So the lumpiness of the universe requires some initial lumpiness to get it started, to get things started clumping together. And it turns out that if we model the expansion of the universe, the lumpiness that we see in the cosmic microwave background, here's a more recent map from the Planck satellite, which was launched in 2011, 2012, started taking data in 2013. Notice that these maps all show the same features, just with higher resolution. It's like getting a digital camera with bigger and bigger pixels, so we can, or more and more pixels, so we can measure that structure at smaller and smaller scales. Not only do the wavelengths and energies of this light correspond to exactly what the Big Bang model says they should be, the degree of anisotropy, the degree of fluctuations, the degree of lumpiness in the data is exactly what the Big Bang Theory needs in order to give us a universe that looks like our universe today. What is our conclusion from this? Our conclusion from this is the Big Bang model is based on evidence. The evidence of cosmic redshifts, the distances to galaxies, all determined using the tools of astronomy we've been talking about. The prediction of the Big Bang Theory, that the universe was once small, hot, and dense, and filled with radiation that should still be bouncing around the universe, has been confirmed by experiment repeatedly over the past 50 years or so. So, one of the things that I stress again and again in a course like this is the relationship between theory and experiment, the relationship between evidence and explanation. Our evidence of the redshifts of the galaxies is explained by the Big Bang model. The prediction of the Big Bang model is confirmed by the evidence of the cosmic microwave background and other bits of evidence as well. For example, one of the things you can talk about is if the whole universe used to be small and hot, there was a point in time where the whole universe would have been as dense as a star and as hot as a star, which means there was a little time in the history of the universe where it was hot enough everywhere in the universe for nuclear fusion to happen. Nuclear fusion is the process that happens in stars where hydrogen is fused into helium. If that's true, then there should have been a little window of time where everywhere in the universe was fusing hydrogen into helium. We can take our Big Bang model, calculate how long that period would have lasted, calculate how much hydrogen would have fused into helium, calculate how much of the current universe should be helium, use spectroscopy to observe the universe by looking at galaxies that are 10, 11, 12 billion light years away, so they're pristine, they're from right after the Big Bang. Measure the ratio of hydrogen and helium to the universe, and it turns out that that ratio is exactly what the Big Bang model predicts it should be. So there are multiple intertwining bits of evidence, all coming from the same handful of tools that we've talked about in the class. So what we'll talk about next is we'll take a step back to the smaller scale. We'll talk about stars and galaxies, and we'll put the cosmology aside and come back to it at the very, very end of the course when we talk about what are the unanswered questions about the Big Bang model. The most important one being, why did the universe start expanding, and where did it come from, and where did that very hot, dense initial state come from? We don't have an answer to that yet. In fact, we don't even really have theories for that yet. So the Big Bang model gets us back to a certain point in time before which we don't really know what's going on. And a really interesting question that arises from that is, can we imagine evidence that is still able to be observed that could get us back to that moment of the Big Bang expansion?